So an exponential function is one that can be written as a to the x. We've got some restrictions on this. Let me correct that. It's a raised to the x. So this is a little different from what we normally do. We're not used to having our variable a as the exponent. So we're going to learn how to handle that. Of course, a in this case, the way that the author has defined it, has to be greater than 0. In cases where a is less than 0, then we'll see that we get a reflection of our basic graph. And also we say that a is not equal to 1. Why wouldn't we have a equal to 1? 1 raised to anything is just 1. It's not interesting. So we're looking at everything except 1, and of course a is greater than 0. So this is our basic function. The domain of this function is all real numbers. We can plug in anything for a to the x, and then we're going to talk more about what the range of the function is. All right, so let's evaluate some of these expressions involving exponential functions. All right, when it comes to evaluating, we simply need to plug in. So we've got f of x equals -2 to the x plus 1. And so if we plug in, we get f of 3 equals -2 raised to the 3 plus 1. With this negative, is the exponent applied to it? Yes or no? No, it's not. Okay. The exponent's not applied to the -2. If it was, then we'd have to write it this way, but that's not what we have. So our final answer, we can already tell, is going to be negative. We're looking at 2 raised to the 4th power, which is just what? -16. Okay, g of x equals 6 raised to x minus 1. Okay, let's say we're interested in g of 2.8. So we just plug in. Okay, this one we can't, at least I can't do in my head. And so we can use our calculator. 6 raised to 1.8 is what? Okay. 25.16. Okay. And then here we have g of x equals -2/5 raised to the 3x minus 1. Let's say we're interested in, we'll make it simple, g of 1. So we've got -2/5 to the 2nd power, and so that gives me -4/25. Okay, questions about that? All right. Next thing we want to look at, it says find the exponential function of the form f of x equals a to the x that contains the given graph point. All right, so basically we're doing some modeling. They tell us that this is an exponential function, and when we hear that, we need to think about this particular form. F of x equals a to the x. Excuse me. All right, so we're going to plug into our model. And so we get f of x equals a to the x. Okay, in this case, f of x comes out to be 1/9. and then we're looking at a to the negative 2. So we're trying to figure out really what a is, what the base is. And so we can think about different ways of writing this. Of course, if we use our exponent rules, we can rewrite a to the negative 2 as what? If we wanted to use a positive exponent. Not to the 1/2. 1 over a squared. Okay, so if we think of it that way, then a must be equal to what? 3. Okay, we could say, and this is what we'll start to do when we're trying to solve this type of problem, we'll try to have the same base on each side. So we've got 1 over 9 equals 1 over a squared, or we could think of this as 1 over 3 squared equals 1 over a squared. So these two things have to be the same. And so therefore a is equal to 3. Okay. Well, I got 3 because I could see when I wrote this as 1 over 3 squared, it was equal to this same expression on the other side, 1 over a squared. We lined things up. We had the 1's, the 1's, the 2's, the 2's. These two other things had to be equal. A equals 3. Okay. All right, what they asked us to find was the actual function. So we would say our function is f of x equals, we said a was 3, so 3 to the x. Okay, and we can check that out when we do 3 to the negative 2, we get what? We should get 1/9. Okay, very good. All right, what about this one? Okay, we've got 1/3 and 1/2 is our point. So we're going to say 1/2 equals a to the 1/3 power. Okay. All right, with this one, we'll do something slightly different. I want to get rid of the 1/3 power. So what could I do to make that happen? Cube each side. Okay, so we get 1/2 raised to the 3rd power, a to the 1/3 raised to the 3rd power. Okay, that causes to be just a 1, the exponent. So we get a is equal to 1. So our function would be f of x equals 1/8 raised to the x power. Okay, questions about that? All right. These two examples are a little simpler than the next example in that we kind of understood the coefficient, the leading coefficient, to be 1. But in the next example, we're going to have a different coefficient. And so we're going to need a little more information. We've got 2 unknowns. We've got the coefficient, and then we also have our base. Okay, but we'll go ahead and solve it anyway. We've got the points 0, 5, and 115. Our basic model x equals c times a to the x. So we'll plug in one of our points for x and f of x. So we get 5 when x is what? 0. Okay, of course, a to the 0 is just not 0, it's 1. 5 equals c times 1, so 5 equals c. Okay. Now I can improve on my model. Instead of just saying f of x equals c times a to the x, we can say f of x equals 5 times a to the x, because we just solved for c. And I'm going to use my second point Okay, and so we get 15 equals 5 times a to the 1. I can divide both sides by 5. We get 3. So a is equal to 3. So our function turns out to be f of x equals 5, 3 times 3 to the x. Okay, and we can check it because each of those points should work in our model. Okay, questions about that? Very good. Yes. I hope. The other thing we could do, if it didn't just wash out like that, is turn it into a system of equations. That would take, a little more work to get it, but if we had 2 equations, 2 unknowns, we could solve for those. Yes. Another one like that? Okay. Okay, so if we have the points 0, 3, and 2, 12, okay, and our basic model is f of x equals c times a to the x. Okay. I'll plug in 0, 3 first. So we get 3 equals c times a to the 0. A to the 0 is 1, so we get c equals 3. Okay, that brings our model to f of x equals 3 times a to the x, and this time I'll use the point 2, 12. So we get 12 equals 3 times a squared. Okay, if I divide both sides by 3, we get 4 equals a squared, or a equals what? 2. Okay. So our model looks like f of x equals 3 times 2 to the x. Okay. Questions about? Yes. Because the x is just on the base. Okay, and this is our coefficient. Okay. All right. Did we skip something? No? Okay. All right, so here's some properties of exponential functions that we should be aware of. It says an exponential function, f of x equals a to the x. Okay, is defined for all real numbers x. Okay, we already said that. Domain is all real numbers. We can plug in anything. The graph of an exponential function is a continuous, unbroken curve. The rules of exponents hold for all real numbers. So, just in case you've forgotten some of those rules, we're going to go back over those very quickly. But these are some basic properties for our exponential functions. So, for a, b, x, and y, real numbers with a greater than 0 and b greater than 0. Remember, if we multiply exponential expressions that have base, what do we do with their exponents? Add. Okay, so a raised to x plus y. Okay, if we have the same base, what do we do with the exponents when we divide? Subtract. Okay. Here we have a times b raised to some exponent, so we can actually distribute the exponent to each of the factors. So this becomes a to the x times b to the x. Okay. And then here we've got an exponential expression raised to a power, so what do we do with the exponents? Multiply. Okay, a raised to the x times y. All right, we've already used this several times today. A to the 0 is 1, okay, as long as it's not equal to 0, and of course in our definition it's not. And then a to the negative x is equal to what? 1 over a to the x, or we could write that as 1 over a to the x, taking advantage of our quotient rule, kind of going, not the quotient rule, actually we didn't write that rule up here. I guess we could write another rule. If we have a over b to the x, then that's going to be a to the x over b to the x. We can distribute that exponent to our quotients, okay, just like we could to a product. All right, so you want to be familiar with those rules because we'll be using those. All right, we want to be able to graph our exponential functions. And so let's just take a look at a couple of graphs and then we'll make some comparisons. Okay, we're going to look at x values of -2. Let's do -3, -2, -1, 0, 1, 2, and 3. Okay, and let's graph 2 to the x first. Okay, so if we do 2 to -3, that's the same thing as saying 1 over 2 cubed, or 1/8, right? If we do 2 to the -2, we're going to get what? 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1, 2. 2 squared is 4, and 2 cubed is 8. Okay? All right, so let's see if we can plot some of those points. All right, so this is the graph of f of x equals 2 to the x. Okay, what are some things that you think might be important to note about this graph? And especially anything that we might be able to say in general about 2 to the x or a to the x. Will it ever take on negative values? No. No matter what we put in, whether it's a negative number or a positive number, it's never going to take on negative values. It's never going to equal 0. Okay? What else do we note about this basic graph? Okay, let's think about that. We'll go ahead and look at the second one and see what we get. Okay, if 1/2 to the -3, okay, that's the same thing as saying 2 to the what? 3rd power, or 8, right? All right, and so then 1/2 to the -2 is going to be 4. 1/2 to the -1, 2. 1/2 to the 0 is 1. Okay, 1/2 to the 1 is 1/2, 1/4, and 1/8. Okay, so backing up and graphing this one, okay, at -3, it's up at 8. Okay, at -2, it's at 4. At -1, it's at 2. Okay. Then again, we come right here to 0, 1. Okay. What else? 1, 1/2. Then 1/4. And then 1/8. Okay, so it looks something like this. Okay. All right, again, we can say that the graph is always going to be what? Positive. Okay, it's always above the x-axis. Which point did it go through that our other graph went through? 0, 1. That's always going to happen. No matter what the base is, f of x equals a to the 0, that always comes out to be 1. Okay, so the basic graph always goes through 0, 1. Okay, and what happens when we went through 1? For 2, when we were looking at 2 to the x, when we plugged in 1, we got what? 2. Okay, when we plugged in 1 to g of x equals 1/2 to the x, we got what? 1/2. So it looks like the point 1a in general will always be a part of the graph. Does that make sense? Whatever the a is. When the a was 2, then we got 1, 2 as a part of the graph. If we made that a 3, 1, 3 would be a part of our graph. Okay, when we looked at 1/2 to the x, 1/2, or rather 1, 1/2 was a part of our graph. Okay, and this one we would call 0, 1. Okay, very good. So let's see what generalizations we've left out. Okay, first of all, the domain of f of x equals a to the x, we already said was all real numbers. Okay, so all real numbers, so minus infinity to infinity, if you want to state it that way. Okay, the range is going to be let's say f of x, let's say 0 to infinity. Okay, the entire graph we saw lies above the x-axis. Okay, for a greater than 1, f is, this should say, an increasing function. So the graph rises to the right. Okay, that's what we saw here. Okay, for this one, as we go to the right, the function is increasing. Okay, as x goes towards infinity, y goes towards infinity. As x goes towards minus infinity, y goes what? 0. Very good. Okay, because that was kind of like an asymptote for the graph. Okay, for 0 less than a less than 1, f of a is what kind of function? Decreasing. Okay, that's what we saw right here in the red graph. As we go from left to right, the function actually decreases. And so as x approaches infinity, y approaches what? 0. And as x approaches negative infinity, y approached infinity. Okay, the x-axis is a horizontal asymptote for every exponential function of the form f of x equals a to the x. For each exponential function, f is 1 to 1. So if a to the u equals a to the v, then u equals v. We used that property a little bit earlier, and we'll use it again. Also, f has an inverse. Okay, that's going to be logarithmic function. We'll talk about that later. And then it says the graph of f of x equals a to the x has what kind of x-intercepts did we see? None. It has no x-intercepts. So it never crosses the x-axis. No value of f of x equals a to the x causes this thing to be 0. Okay, it's never equal to 0. The graph of f is a smooth and continuous curve, and it passes through the points minus 1. That's going to be 1 over a, 0, 1, and 1a. Okay, those are the basic points. Is that everything on? Okay, good. All right, so these are things we should be familiar with when we look at the graphs of f of x equals a to the x. Okay. All right, we can also use our shifting to help us see what's going on with the graphs. We've talked about this earlier. If we do f of x minus b, then that's going to cause us to shift the graph which way? To the right, okay, when b is positive. Okay, we've got the vertical shifts and stretching and compressing, and also the reflections. So let's see if we can get a few graphs done. Okay, we want to graph g of x equals 3 to the x minus 1 minus 2. Now we might think about what the basic graph looks like before we deal with the minus 1 and the minus 2 part. Okay, so let's sketch in. Okay, we already said that 0, 1 is part of the basic graph. Also, when we go to 1, for this one, we should be at what? 3. Okay, and if we decide to look at negative 1, we should be at 1/3. Okay, so this gives us an idea about what the basic graph looks like. Okay, if we did 2, we'd be all the way up at 9. So it goes up pretty rapidly. So let's say like that. All right, but this one, we can expect that the graph is going to shift which way horizontally? Okay, shift right. One unit, and which way vertically? It's going to be down 2 units. Okay, so now that we've got a few key points, we can actually use this to move those key points. We had a point at negative 1, 1/3, so I'm going to walk that 1 unit to the right and down 2 units. So that brings me right here. Okay, if I take this one, walking 1 unit to the right, down 2 units. Walk, which one? This one, 1 unit to the right and down 2 units. And I can even do that with my asymptote. We had an asymptote for our basic graph right here, right? I'm going to shift that how? Just down 2 units. Okay, so my new asymptote is 1, 2. All right, and that's enough for us to get a good sketch of our graph. It looks like this now. The yellow graph was just our basic graph of 3 to the x. And so we used those 3 key points that we listed in item 8 to help us get that graph. Okay. All right, what about g of x equals 2 times 3 to the x plus 1 minus 1. I'm going to give you a second to try that one on your own. Try doing the basic graph and then going from there. Okay, so what are we expecting to happen here? We're going to shift which way? Okay, we're going to shift left 1, and then also down 1, and what else? We're going to stretch which way? We're going to stretch this vertically away from the x-axis. Okay, so, and we'll probably do that, I'm trying to think, do that first. So basically multiply each y value by 2. Then we're going to shift left 1, down 1. Okay, so we were at 1/3. I'm going to do 2/3. Now I'm going to shift left 1 and down 1. So that puts me about right here. Okay. We had another point here at 0, 1. So that would become a 2. But I'm going to shift it left 1 and then down 1. All right. Also, we've got, what else? Okay, so we're going to multiply that by 2. That gives me 6. And then I'm going to shift left 1, down 1. Okay, so our graph, here's my asymptote. I think I can just shift him down 1, I hope. And so it looks like this. Okay, questions about that? Say that again. We do, but we shifted it down. So the basic graph doesn't have an x-intercept, but once we start to shift this thing up, down, or whatever, we might have an x-intercept. Okay? All right, other questions? Well, not just positive, but because it's greater than 1. If this had been a 1/2, then we would compress it towards the x-axis. Okay? But it should look, I don't know if it looks that way, but it should feel like it's been stretched out vertically a little bit more. Okay? All right, other questions? All right, very good. Okay? In the next one, they want us to come up with some equations. And we want to write an equation of each graph in the final position. So they give us the graph of y equals 3 to the x is reflected in the y-axis and then shifted 3 units right. Okay, so if we reflect in the y-axis is our vertical axis. Okay, so that means we're going to flip it over this way. So what becomes negative, the x values or the y's? The x values, right? So our function, our new function is going to look like y equals 3 to the negative x. Very good. Okay, it says then is shifted 3 units to the right. So we're going to say what? Minus 3. Okay. Questions about that? All right. The graph of y equals 2 to the negative x is reflected in the x-axis and then shifted 3 units up. They've already given us one that's y equals 2 to the negative x. So if I want to reflect about the x-axis, okay, then what becomes negative? The entire function, right? So we get y equals negative 2 to the negative x, and I did that because that was already there. And then we're going to shift 3 units up, so we do what? Plus 3. Okay, very good. Alrighty, any questions about how we came up with those equations? That goes back to our first chapter that we talked about with shifting and stretching and all of those things. That's right, because this piece gives us our y's, right? And so we want to make basically the y's negative, so we put it out front. Okay? All right, we want to solve some equations, and this goes back to that principle that we mentioned a little bit earlier that says if we have, let me scroll this up, if we have a to the u equals a to the v, then this implies that u equals v. So when it comes to solving problems like this, if I can, I'm going to try to write each side using the same base. If I can do that, then that means that the exponents have to be equal, and we can solve it from there. So for instance, when we get 9 to the x and 243, and let me stop for a second and do something that should help us. We should be familiar with powers of a few numbers. Okay, so obviously 1 squared is 1, 2 squared is 4, 3 squared, and actually that's not how I want to do this. Okay, we already said 1. Am I doing this right? I want us to look at powers of 3. So maybe I had it powers of all of these numbers. Maybe I had it right the first time. So when we do 1 squared, we get 1. 2 squared is 4. 3 squared is what? 9. 4 squared is 5 squared. Okay, 36, 49, 64. 81, 100. Okay, if we talk about cubes, we're going to get what? 1, 8, 4 cubed is, okay, 5 cubed is, okay, 6 cubed is 216, okay, 7 cubed is what? 343, okay. All right, 8 cubed is 512. Okay, that might almost be enough. 9 cubed is what? Okay, 729, and obviously 10 cubed is 1,000. Okay, and we might even need to know some of these to the 4th power. The point is we got to kind of be able to think backwards when it comes to writing these things using a particular base. Okay, so when we go back over here, we've got 9 to the x. We've got 243. Was 243 in our list anywhere? Okay, we saw it where? Okay, let's make sure. Okay, we probably need to look at some more powers of 2 and 3. Let's stretch these out. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th, okay, 2 to the 8th, okay, 256. All right, with our cubes, we've got 3 cubed. 3 to the 4th is what? And 3 to the 5th is 243, okay? And we could do some more, but certainly with 2 and 3, we want to make sure we're aware of the different powers because we're likely to see a lot of those. So, now, I can write this. I can rewrite 9 as what? Okay, 3 squared raised to the x, and that becomes 3 to the 2x. And if we're familiar with powers of 3's, then 243 can be written as what? We just saw 3 to the what? Was it 5? Okay. 3 to the 5. All right, so now we can say 2x equals 5, or x equals what? 5/2. Okay, but once we were able to write these using the same base, then figuring out or solving for x was very easy. Questions about that? Okay. All right, here we have 3 again. We've got 3 to the negative x, also equal to 27. 27 is what power of 3? Okay, 3 cubed. So we can say negative x equals 3, or x equals negative 3. Okay. 4 to the x minus 1. Okay, well, what are we going to do with this? Can we write each side as a power of 4? Say just what, x equals 1? Okay, and why can we say that? Okay, 4x to the 0 is 1. So maybe we might write 4x minus 1 equals 4 to the 0, right? And so, yes, x minus 1 equals 0, or x equals 1. Alrighty. Okay, what about this next one? We have the square root of 2 raised to x. Well, the square root of 2 we can rewrite as what? 2 to the 1/2. Okay, raised to x. We've got 1 over 16. Can we write that using a base of 2? Four. Okay, 2 to the negative 4. Right? 1 over 2 to the 4th is 1 over 16. So it's 2 to the negative 4. So we get 2 to the 1/2 x equals 2 to the negative 4. 1/2 x equals negative 4, or x equals negative 8. Okay, questions about that? All right, see what you can do with E and F on your own. Okay, what'd you do with this one? Okay, they weren't quite the same basis, but how can I make them the same basis? Multiply by negative 1? Not quite. What could I do with the exponent that would flip this over? Make the exponent negative, right? So if I do 2 over 3 to the negative 2, that's the same thing as 3/2 to the positive 2, right? That negative exponent causes the entire thing to flip. It's still cubed, but now I have the same basis. I've got 2/3 to the x and 2/3 to the negative 6. So we get x equals negative 6. Okay, questions about that? Okay, in short, a over b raised to x is equal to b over a raised to negative x. Okay, if we just make the exponent negative, it flips the entire thing. All right, we got 5x squared equals 1 over 25 to the negative 8. So we got 5x squared. 5 is going to be our base. We can write 1 over 25 as what? 5 to the negative 2. Okay, and we got the negative 8 on the outside. So we get x squared equals 16x equals plus or minus 4. And that would be our solution. Okay, questions about that? Okay, very good. All right, that's the basics of section 1. Section 2, we're going to look at some applications and get ready to talk about the exponential function. First, we're going to talk about simple interest. And so our formula for simple interest is I equals PRT. Okay, I equals PRT. It says the simple interest I on a principal P. Principal is what we invest, or it could be what we borrow, depending on which end of the table you're on, at a rate R, which we express as a decimal, per year for T years is I equals PRT. This is not compound interest, very just simple interest. Okay, the accrued value of an investment or loan at simple interest after T years is A of T equals what you started with. That P is the principal that we started with, plus the interest that we've earned. Or if we factor out the P, it equals P times 1 plus RT. So it's what the entire value of the account is. So we've got some examples here. Find the simple interest and amount for each value of principal P, rate R, per year, and time T. Okay, so we've got a principal of $10,000, a rate of 5%, and the time is 10 years. So our interest is PRT, where the principal is $10,000. The rate is 0.05, and time is 10 years. So we just multiply those together. And we get $5,000 in interest. That would be nice. Okay, and then so the total value of the account is what we started with plus the interest that we earn. So we started with what? $10,000, and we earned interest of $5,000. So we get $15,000 is the accrued value of the account. Okay. All right, in B, basically the same situation, except this time we've got 6 years and 3 months. So how are we going to write time when we have months here? 3 months is how much of a year? A quarter. Okay, so we can say this is 6.25 years. And so our interest is principal times rate times time. So 8,620. Our rate in decimal is what? Okay, very good. And we just said the time is 6.25. Okay, I got 3,070.89 for interest. Okay, so my accrued amount would be 8,620 plus this 3,070. I get $11,690 and 88 cents. This should have been an 88, right? Okay, 88 cents. Okay, very good. Questions about that? Okay, good. All right, when we have compound interest, at certain intervals, the interest that we've earned gets added to the principal. So, the larger the principal, the more interest you get. And so as we go along, instead of getting the same amount of interest based on the original investment, the invested amount increases, and so does the interest. So compound interest is better if you're an investor. So we get A equals P times 1 plus R over N raised to the NT. A, again, is the amount, total amount or value of the account after T years. R is going to be our rate expressed as decimal. P is still the principal. T is the number of years. N is going to be the number of times that the interest is compounded each year. So if it's annually, it's just once a year, semi-annually, twice, quarterly, 4, monthly, 12, daily, 365. Okay? So how does that work? Okay, find the future value of the given principal P and the interest earned in the given period. Okay? So we've got a principal here of $8,000 at 6.5% compounded daily for 15% or 15 years. Okay? So they gave us one formula. It was A equals what? P times 1 plus R over N raised to the NT. Okay, our principal is 8,000. Our interest rate is 0.065 divided by the number of times that we're going to compound, which is what in this case? Daily, so 365. And we raise that to 365 times 15. Okay, put that in our calculator carefully. Okay, so we've got 8,000 times parentheses 1 plus 0.065 divided by 365 close parentheses, and that's what we're going to raise to 365 times 15. Okay, and so you should get, oh, I got an error. Let's see what I do wrong. Oh, is that what it was? Okay. Second insert parenthesis. Okay. Go to. So delete this. Oh, 8,000 times. Gotcha. Stop it. Okay, second insert parenthesis. Is that better? Cross my fingers. Did you get 21,207 and 50 cents? Okay. $7.50. Okay, very good. All right. Again, we've got P equals $8,500 at 7.5% interest compounded monthly for 12 years. Oh, by the way, they also wanted the interest in this one. So how would we figure out how much interest was earned? If this is what we have now, okay, subtract what we invested, right? Our interest is going to be the accrued value minus our investment. So we had $21,207.50. We invested $8,000. So that brings us down to $13,207.50. Is that right? Okay, good. All right, accrued value here is going to be 8,500. Our rate we'll write as what? Okay, all right, 0.075. We're going to divide it by 12. We're going to raise this to 12 times 12. Okay. All right, so that should get it for us. Yes. Okay. 128,000. Okay. All right. Well, let's do it again because the calculator can be a little tricky. We got to make sure we put it in just right. We got 8,000. Okay. Then I didn't put my parentheses, my first one. So 1 plus 0.065 divided by 365, close parenthesis. Then I'm going to raise this to a power. Now, with this operating system, you know, it gives me that little exponent thing. If I was using my calculator, I would put another set of parentheses if I didn't multiply those out already. So maybe that's why you got a different answer. Otherwise, it only raised it to the first number, and then it multiplied your answer by the second. So make sure that your exponents 365 times 15 are grouped together. Okay? You understand what I'm saying? All right, so when you did that, I got 21,207.50. Okay. You have to make sure that that exponent, if you're going to have it multiply it for you, is grouped together. Okay? All right, and with this one, we get 8,500, okay, times 1 plus 0.075 divided by 12 raised to the, I know that 12 times 12 is 144, so I just did that in my head. So I got 20,848. Is that what everybody got? Okay, and our interest on this one will subtract 8,500. Oops, I subtracted too much. Plus 8,500. 85,000. I got $12,348.15 is the interest. Okay, questions about that? All right, let's talk about, do we have time? A little bit. Okay, let's talk about continuous interest. Okay, basically, I don't know if we mentioned this at all yet, but obviously the more often we compound, the better, right? And so what's better than daily? You know, every minute, every hour, what? Well, somebody who had a lot of time sat down and thought about it and found the best compounding, and this is where the number E comes from. I think we'll define it officially a little bit later. But as we increase that compounding, this little value comes up, and we'll talk about it a good bit. The formula for continuous compound interest is A equals P e to the RT. And I'll show you where that is on your calculator in two different places, just in case you don't know. Okay, but we got P equals 6,500 at 8%, compounded continuously for 15 years. So we get A equals 6,500 E raised to the 0.08 times 15. Okay. And so on my calculator, I've got e to the x here on my natural log key, the ln key. I also have just e without any exponent built into it on the division key. So either one of those would work. But we're going to do 6,500, okay, times e. It gives me a place for my exponent, so I'm going to do 0.08 times 15. I actually didn't need that. Okay, and so we'll hit enter. I get $21,580.76. That's my accrued value. My interest, I would subtract 6,500 from that to get $15,080.76. Okay. Questions about this? Well, basically the same thing, except you just gotta put this in parentheses. That's all. Everything that you're raising to the power, if you're doing some multiplication or something else, you need to make sure all of that's included in parentheses. Up to find the interest. That's right. Okay. All right. Let's do one more. It says find the principal P that will generate the given, that should say, future value A. Okay, I'm not sure if we can quite do this yet, but we'll set it up anyway. So you got to send your child to college or something like that, okay, not college. What can we do at $10,000? Buy them a little itty bitty car. Okay, so you need $10,000 in the future. At 8% compounded quarterly for 10 years. Okay, so how do we set that up? First of all, we've got A equals P, 1 plus R over N raised to the NT. Okay, what we're trying to figure out is what the principal is. At the end of this 10 years, we need $10,000. Okay, we've got a rate of 8%, so that's 0.08. We're compounding quarterly, so we're going to divide by what? 4. Okay, raised to the 4 times 10. Okay, and for your calculate, well, you're going to just put in 40. All right, so we get 10,000 equals whatever this is. So what's 1 plus 0.08 divided by 4. Raised to the 40. I got 2.208 approximately. Okay. All right, I'm going to divide both sides by 2.208. So 10,000 divided by second answer. I got P equals $4,528.90. Okay. Questions about that? All right, we'll look at some more future value stuff. Hopefully you see that